All right, so welcome everybody, and welcome our speaker Albert Visser, who will talk about cyclic Henkin logic. Is there life beyond the third Löb condition? Now, Albert is somebody that needs no introduction, but despite this, we have invited his former student, Joosten, to give him an introduction. So Joost, please tell us a few words.
Okay, thank you very much. It is my pleasure to introduce Albert Visser as the person. So I want to congratulate the organizers of this seminar to being able to attract all these high and eminences to give presentations here. So as you mentioned, I am a former student of Albert Visser. So I'm not his first PhD student, but I think I was his first PhD student as Albert being full professor. So it's a privilege to have studied with Albert. Albert is, I got to know Albert, a specialist in interpretability logics, where he dominates the fields and actually set it up himself. But it turns out that Albert is a specialist on many more fields. So he comes from mathematics. He studied mathematics in the Netherlands and later did a minor also in philosophy. Did his PhD with big names as Van Dalen and Barendrecht. And when I was 4 years old, Albert Visser graduated, obtained his PhD with the highest distinction, cum laude. Well, it took me a little while going from 4, when I was, I think, 26, I joined Albert Visser as a PhD student in Utrecht University, where shortly after he became full professor. As I told you, Albert Visser is an eminency in interpretability logics, but he has many more fields of interests, and that characterizes big scientists. So he is also an expert on paradoxes, on intuitionistic mathematics, on modal logic in general, and truth, theories of truth. Many fields are inhabited and, if not dominated, by Albert. So I feel privileged that I learned so much from Albert, and not so much only techniques, but Albert Visser is always, original in his just finds new expected methods, and so I'm looking forward to this talk here. And Albert is typically combining in his work from whatever, computability, model theory, category theory, but central to his research, modal logics. Proof theory, excursions, no problem for Albert. And I think many of the things that I've mentioned here will come together in this talk. So Albert Visser, an eminence in logic, and I'm looking forward to hear your talk, Cyclic Henkin logics. And I hope that because I have to get my vaccination, so I have to leave in an hour, but I hope that I hang on for long enough to hear if there is indeed life beyond the third Löb condition. Albert, the floor is yours.
Okay, thank you very much, Joost. I have to admit, I always feel a bit shy when I hear all this praise. But anyway, yeah. Of course, I wouldn't have asked the question when the answer would not have been yes. But okay, so we are going to see it. So for those who didn't attend my previous talk, here to the left, you see Martin Löb, and here to the right, you see Henkin. And of course, this is then the ghosts of what is left after the third Löb condition is omitted. Okay, now let's try to, oh yeah, so moves. Okay, so first let's have a look at the Löb conditions, right? So the Löb conditions are well known. It's that if phi is provable, then the provability of phi is provable. Secondly, if an implication is provable, then we can move the implication out. So then, from provable phi implies psi, we have provable phi implies provable psi. And the third one is the formalization, the internal version of the first one, namely, if provable, then provably provable. So yeah, this talk is not about that, but yeah, the work starting with the Löb conditions has been technically extremely fruitful. It led to a lot of research. It created provability logic, and of course, from provability logic, we got all this research on Jabarits's logic, etc. But also, philosophers have taken a fancy of the Löb conditions, thinking that they're a necessary condition for a predicate to count as a provability predicate at all. So I'm not going to talk about all these issues, but just about circumstances in which the conditions fail. Well, if you think about it, the first and the second are, well, they already hold in extremely weak systems. You don't, there's no, so they're in some sense very primary, right? So they're also the axioms of the basic modal logic K. So the third Löb condition is the problematic one. The verification of it is already a little bit more difficult, and you can find circumstances in which it fails. But moreover, so one of the most important applications of the Löb conditions is the proof of the second incompleteness theorem. So G2, and but if you study it, you can have G2 also in many cases where the Löb conditions fail. And so, yeah, so that leads us to the question, what happens if we drop the third Löb condition? So is there still life? Okay. Okay, so I'm not going to say much about this example, but just to illustrate that this can happen. So look at elementary arithmetic, which is I delta 0 plus the totality of exponentiation. So you can find a sigma 0, 1 numeration of the axioms of elementary arithmetic in elementary arithmetic. And that has the following properties. So EA believes that this set of axioms is finite. Of course, the finiteness is only internal, so it's not, so that there's no external numeral that bounds the set of axioms. Also, what you do not have is that from the provability of consistency, we have the inconsistency, so the verifiability of the second incompleteness theorem fails for this enumeration. And at least for me, amazingly, all Gödel sentences are equivalent to the consistency of inconsistency, but not as usual to the simply to consistency. So you see that it's already, so elementary arithmetic is a very solid theory, sigma 0, 1 numerations. It's so that you enumerate the axioms by a sigma 0, 1 predicate is a kind of logical thing. And so that you see that even in these rather acceptable circumstances, the Löb conditions may fail. Yeah, so suppose that you have an interpretation of an extremely weak arithmetical theory. So I think the main claim to fame of this theory R is that you can verify the fixed point, the Gödel fixed point lemma. And suppose you have the Löb conditions for any predicate, then you can derive Löb's principle, namely box. So box phi implies phi, then box phi. So if you think about the things modally, what you can see is it works as follows. So Löb's principle plus the Löb's conditions gives us Löb's logic. So Löb's logic is the same thing as the basic logic K plus Löb's principle, and so that's somewhat surprising. So it turns out that the third Löb condition, so provable implies provably provable, is derivable from Löb's principle, and so that's by a little argument that was discovered by Dick de Jong. So Löb's logic is closed under Löb's rule. So what is Löb's rule? It says that that if you can derive box phi implies phi, then you can derive phi. So that's Löb's rule, right? So it's so as the third Löb principle provable implies provably provable is an internalization of necessitation rule. Löb's rule is an externalization of Löb's principle. And so Löb's logic is also equivalent to K plus 4, which is the principle, or which is the same thing as the third Löb condition. So K plus provable implies provably provable plus Löb's rule again gives you GL. But you see there's a difference between Löb's principle and Löb's rule. So they're equivalent over K4, but over K they're not equivalent because over K Löb's principle proves provable implies provably provable, so the third Löb condition, but over K Löb's rule does not do that. In fact, K is closed under Löb's rule. So if you can derive provable phi implies phi in K, you can also derive phi, and that you can prove by a trivial Kripke argument. So so those are the main players. Okay, so now the theory of fixed points. So we say that phi is modalized in P if all occurrences of P are in the scope of a box. And now in Löb's logic, you have unique and explicit modalized fixed points. So there's this algorithm to produce an explicit fixed point for any formula in which the fixed point variable is modalized, only occurs in the scope of a box. So if we go to so our aim is to study the Henkin calculus. If we study the Henkin calculus, we lose the explicit fixed points, but we still do have uniqueness. Okay. Now we move to the study of cyclic Henkin logic, and I will do this a little bit, build this up in stages. So the basic idea is extremely simple. What is cyclic Henkin logic? It's simply K plus Löb's rule plus fixed points. But so the devil is in the details. So what do we mean with fixed points, right? And in fact, you can do this in all kinds of ways. And it was, and thinking about these ways and trying to understand what the differences are with respect of these ways it is surprising if you really start to think about what's going on here. So one idea, and that you really find in the literature, is simply because we don't have explicit fixed points anymore, right? So if we have Löb's rule only, and not the third Löb condition, provable implies provably provable. So you have to do something, and so one thing you can do is add it as constants. So this has been done in the literature, but the problem with the constants, because they don't have, they're not polynomials. The problem with the constants is really that that the resulting thing that you get is not the logic anymore, right? It doesn't satisfy the substitution rule. So I think this is, for many practical purposes, adding the constants is fine. It's a solid way to do the things, but it's not, theoretically it's less beautiful, because you lose the fact that the logic that what you are studying is a logic. So a more sound way of doing it is adding the fixed point operator, and that's in fact what I do in another paper. But it has you're really punished for the fact that you need the whole circus of binding conditions to, because if you have the fixed point operation, you introduce the binding of variables, and you get problems with substitution. You need to change bound variables, so that you have a whole circus, and it's in fact a little bit more difficult. The circus is more problematic than in the case of ordinary predicate logic. So the fixed point operator is in a sense, of course, the obvious way to do it. But yes, so you have the whole circus of binding, and also there's the feeling that the binding has nothing to do with what is going on, right? It's a kind of external, it's an extra problem that is imposed by your representation, and it's not really internal to what's going on. So now so the third possibility, and that's the one we are going to look at, is use cyclic syntax, and I will explain what that means. So so the theory on the cyclic syntax we call cyclic Henkin logic, and the theory on the traditional syntax with the fixed point operator is the Henkin calculus. And so we are going to zoom in on the cyclic Henkin logic, or CHL. So so the whole idea of using cyclic syntax is not original, and probably I even missed maybe certain independent inventors of the idea, but so I was, at least in my personal history, I was inspired by the really beautiful book by Barwys and Etchemendy on circular propositions. So that's this book, The Liar, and so I really can warmly recommend everybody to read this book. That's really very nice. So okay, so I think I covered some of these things. So why the choice for cyclic syntax? So I already mentioned the negative reasons. If you do the constants, you do not get the logic. With the fixed point operators, you have the whole circus of the theory of binding. But there are also positive reasons. So if you use syntax on cyclic graphs, that will allow you a more visual way of understanding things. For example, and that will be in the next slides, the proof of the multiple fixed point lemma is, well, you don't have to do anything. You just have to look at the picture and you see the multiple fixed point lemma proved. And also many graphs, there's a whole theory of graphs. And so graph theoretical theories ideas become available, right? So these are bisimulation minimality, unraveling, co-induction, and co-recursion. will be suddenly available to prove things. So I'm going to, so my time is too short, so it would be, of course, extremely interesting to go into the co-inductive and co-recursive aspects here, but yeah, I will mainly say something about bisimulation. And so all the other things I will leave in the air, so maybe for a next talk, or you could also read my paper, of course. So here you see graphically how we can solve systems of equations. So now suppose we have two equations, P if and only if phi, and Q if and only if psi. So I'm not supposing that the things are modalized yet, right? I'm now thinking about it in a rather general way. So now we can depict phi and psi as follows. So phi is some kind of graph. So this graph has a root, and psi also has a root. And there are leaves in which we have variables, but the relevant ones are the fixed point variables. So they are P and Q. So I depicted these here on the right-hand side. So note, of course, there could be more P's and there could be more Q's. So I really just choose to represent this as one outgoing arrow with a P and one outgoing arrow with a Q. So how are we going to solve the fixed point equations, these fixed point? Well, this really means that the value of P is made equal to the value at the root, and the value of Q, the value of P is made equal to the root of phi. The value of Q is made equal to the root of psi. So what we do is we simply connect cyclically the P with the root here, and we connect the Q gate, the Q outgoing gate with the root of the psi, and similarly for psi, right? So we connect this one like this, and we connect this one like that. And so this is really the solution. So now if you look at the graph generated when you choose this one as the root, that's the solution for P. And if you look at the graph generated when you use this one as the root, that's the solution for psi. And so you see that, so I think the nice thing here is if you compare this to the usual proof of the double fixed point theorem, so then if you do, in the usual proof, you have to choose an order in which you are going to solve the equations. But this order is in some sense an artifact of the representation. And you see here, there is no order. It's, yeah. And moreover, of course, it's immediately clear, it's really strikes you immediately that this is the solution, and you don't have to no cleverness is needed to solve this system of equations. Okay, so now we are going to give some real definitions. So, so what we need is the notion of a labeled graph. And so now labeled graphs come also in, there's all kinds of labeled graphs. And so, but what we want is ordered successors in our case. So we have the graph. So what does a graph look like? Well, it's a set of nodes. We have a designated root. We have a labeling function that sends every node to a label. So the labels in our case will be simply the logical connectives. Yeah, we will have an arity function on the labels. And so if for example, if the label is conjunction, then the arity of the label will be 2. Now we have the successor function. So if each node of the graph will have a sequence of successors. And so, so this asterisk means that we have finite sequences, including the empty one. For example, if we have falsity, that's zero array, and so falsity will be an endpoint, a leaf, and similarly for a variable. So those will be endpoints. So the set of successors of the sequence of successors can be empty, but for conjunction, for example, there will be 2 ordered successors. And of course, what you demand is that for example, if the node A is labeled with conjunction, and so the arity is 2, of conjunction is 2, then there are 2 successors. And yes, so, and all what we do demand is, but it's not really all that essential, is that our graphs are connected so that we can reach everything from the root. Yeah, now, so in the next slide you will see examples of this. So now so there's an important notion of sameness of graphs, right? So everybody who read a slightly more modern textbook on modal logic will have met this notion of bisimulation. And of course, yeah, so what bisimulation is depends really on your precise notion of graph. Yeah, and so in computer science and modal logic, it's a really important notion of sameness of graphs, right? So there are all kinds of aspects of graphs that we really are only interested in the graphs modulo bisimulation. That's the idea. So now formally a bisimulation is as follows. So it's a relation between the nodes. And so what we ask is that the relation preserves labels. So that's the first one here. And what we also ask is that it preserves successors, right? So if you have the successor sequence, then we want that the corresponding successors in the sequence are also bisimilarly related. So yeah, okay. So yeah, so I'll give some more, slightly more heuristics in the next slide. So yeah, so what we really are thinking is that the true objects, the true formulas that we are going to look at are the things modulo bisimulation. So that's our intended notion of sameness, but it's practical really to not divide it out. And so we will have isomorphism of graphs as our working notion of sameness, right? So that's the idea. It's a little bit like with the rational numbers and fractions. So if we the real objects that we want to think about are the rational numbers, and they are the fractions modulo an appropriate equivalence relation. But for specifying algorithms, etc., it's very nice to have the fractions available, and that's the same thing here. For specifying algorithms, you want to operate on the graphs modulo isomorphism, but of course, what you really want is to only operations that preserve bisimilarity. Okay, so every graph has a canonical unraveling and a bisimulation minimal version. So I'm not just saying this blue thing here for the people who know about this, right? So yeah, two graphs are bisimilar when their canonical graphics are isomorphic, and similarly for the bisimulation minimal version. So this, well, the people who know about bisimulation will understand what I'm saying here. But for the all the others, it's sufficient that so we can there are two different salient ways to choose canonical representatives from the equivalence relations. So let's quickly go to the my examples. So first here we have the liar sentence. So the liar sentence is really, I am not true, so the negation of myself. And so now the liar has an extremely simple representation in cyclic graphs, right? It's simply one node labeled with negation and then the singleton loop on it. But you can do the liar also in a different way. For example, you could have negation here. It has one successor. You can have negation here. Now we can again have the successor with negation, and then we can loop back. We could loop back here, but we could also loop back here. And you see, it's really not if you think about traveling over this loop. But and this one is also not. And so you see that in effect these things are the same, right? So and the idea of bisimulation expresses that. And so the red lines here give us the maximal bisimulation between these two graphs, right? So this single node really corresponds to all three nodes of this. Yeah, so there's no real objection to look at infinite graphs, but we will restrict ourselves to the finite case. I forgot to say that earlier, but that's what we are going to do. We're only looking at finite graphs. So the one, of course, the omega sequence not going down is also is bisimilar to the singleton loop, but we don't allow that one. So here we have the famous Gödel sentence. It says that I am not provable, and it's bisimulation minimal. Its most efficient version simply looks like this. It's negation, then we have provable, and then it's not provable me, right? But we could also do the Gödel sentence like this: not provable, not me. And so if you think about it, it's not box, not box, not box. So that's really the same as this one. And so you have the bisimulation like this, right? So but you see, you only can connect nodes that are labeled negation, and you can only connect nodes that are labeled with the box here, right? So one heuristic idea about bisimulation is that you could think of it as a kind of internal point of view, right? So you could think of the nodes here as a kind of big spheres, and the arrows as one-way corridors that you could traverse. But internally in the spheres, there's nothing that distinguishes them, right? So if you're inside the sphere, the label is written on the wall. So here you have the sphere and the label with the box is written on the wall, but nothing else distinguishes it. So suppose two elves are living in the system. So this elf sees that it has lives in a spherical room with the negation. And so it has one corridor, and then it gets again in a spherical room with the negation on the wall. And similarly for this one, but all these rooms are indiscernible. And so these elves can communicate with mobile phones. But so, and their assignment is to see whether whether their habitats, the country, the buildings they live in differ, but so they, given all the data, you can see that they cannot distinguish this building from that buildings, given that all these rooms are really internally indiscernible, right? So it's the an internal view that you have of the graphs that is the modulo bisimulation view, right? So it's only the local data. What you can do is in a sense relevant. That's bisimulation. Okay, now we are still missing something, right? So if you have the liar, then you're in deep trouble, because you are forced to do something, right? So the liar is not consistent in classical logic, and so that's why it's called the paradox. And of course, there are all kinds of solutions. You can go to all kinds of non-standard logics or whatever. So you can do something to solve the problem of the liar, but yeah, we don't want to go to classical logic, and so we need some solution. And so the whole idea is that there's a guard, and so a guard. So the fixed point phenomenon is in some sense hidden behind the box, right? So the box is a kind of safety valve. It really stops the destructive powers of paradox from forcing us to use a different logic or whatever. And so we need guards. And that's one of the great ideas to block paradoxes is to work with guard. And so now the nice thing is of the cyclic graph idea is that it's extremely simple to see what the condition is, right? So the condition is simply that we only allow formulas in which each cycle contains at least one occurrence of a box. So that's the idea. So a guard in a graph is a set of nodes such that every cycle contains an element of this guard. So I'm not going to say too much about this but it's one of, as I said, it's one of the nice things that we have these things, right? So we have guard induction. So that means that if you have a property on the guard, and if the property backwards propagates from successors of a node to the node, then we have the property on all nodes. That's guard induction. And you have similarly, you have guard recursion. So I will not really explain precisely how this works or give the worked out examples, but I will mention at least where these things are used. Yeah, and moreover, if such a guard is preserved by bisimulation, and similarly for the notions assigned in the recursion to the nodes of the guards, then the values guarded by the recursion are also preserved in the bisimulation. So that's also so nice. So just so if you have good guards, you get notions that are also good for bisimulation. Okay, now I can finally say what the formula is. As labels, we take the proposition of variables and the connectives. A formula, that's a graph with this choice for the labels, and of course with the obvious arities, right? So for example, falsum or truths will be zero array, and we'll have arity 0. And so then a formula is simply a graph in which the set of box occurrences is a graph. So, and as you see from, and that was of course our original motivation, the condition rules out the liar, but it does admit the Gödel sentence. So now we are already and set to define operations on formulas. So what is phi, the conjunction of phi and psi? So remember that phi and psi are now graphs with possibly cyclic graphs. Well, what you do is you take the disjoint union of the two graphs. So of course the nodes phi and psi could share nodes, but since we are thinking about modulo isomorphism, of course this is just a kind of accident of implementation. So what you do first is that you update all the nodes to get the disjoint, and then you add a new root to both labeled conjunction, and the same for the other connectives. So note that there's an overloading, right? I'm using conjunction both as a name for a label and as a name for an operation on formulas. But yeah, I think that's mostly fine. The cost, usually the cost of having, let's say, an overlining here to note that it's an operation, etc. So that makes kind of some kind of horrible thing. Now we have substitution. That's really substituting something for P, for example, will be replacing all the nodes labeled P by the graphs of the thing you substitute. So identifying the node labeled P with the root of the graph. The fixed point operator is simply the result of identifying all node labels P with the root, where the root keeps it labeled. So it's important. So you can only form the fixed point of the fixed point operator only works if phi is modularized in P, because otherwise you would create a cycle in which on which you do not have a box, right? So interestingly, so the fixed point operation only gives you formulas that satisfy the guard condition, namely that on every cycle you have a box, if all occurrences of P and phi are in the scope of a box, right? So here the kind of restriction on the fixed point gets out automatically from the restriction that we have on the formulas. Now we also have something that is really something like an indeterministic, non-deterministic subformula, namely that P be any fresh variable. So the phi lightning P is simply the result of diverting all the incoming nodes of the roots to new node labeled P, right? So what you do is you make the node the root non-cyclic, and everything that would end in the root goes to the fresh variable P. So that's the idea. So that's really so. So if you view the phi as a fixed point, it's really the subformula of which phi is the fixed point, so to speak. But of course, in our context, that's a slightly different thing, right? You obtain this non-deterministically. Okay, so it's good now to stare a little bit at conjunction. So so a graph is a conjunction. That doesn't mean that it is modulo isomorphism generated by the operation conjunction. So here we have the graph that says P and box me, right? So this is really a formula because we only have this cycle, and there on that cycle we have a box. So this is an okay formula, and it's clear what it means. It's a conjunction, so that at the root is labeled with a conjunction. Now we can form the conjunction as we can apply the operation conjunction at to P and box me. So we may take the conjunction of P and of this other formula with root box. And so then you get and this, right? You get P and box, and then conjunction P and box B. And so you see that these two things are bisimilar. So correlate this to this, P to P, P to P, this with this one with the box to that one and to that one, etc. Right? And so that easily verified that that's a bisimulation. And so you see that P and box me is not, so you have graphs on that are not generated modulo isomorphism by the operation of conjunction, but modulo bisimulation, the graph is generated by the operation of conjunction. And that's the general case. So all our operations are bisimulation invariant except the lightning. So applying the lightning, you get a formula that's modularized in P. That's because you cut off all the cycles to the root and divert them to P, but on those cycles there should be a box. Yeah, phi restricted to P has more nodes, but it has less cycles, and that's kind of important technical fact. Okay, so here we have the important insights. So suppose the main connector of phi is conjunction, and the formulas generated by the successors of phi are psi and chi. Then phi is bisimilar to psi, the conjunction of psi and chi, and similarly for the other connectives, right? So this tells us really that all formulas can be generated modulo bisimulation from the atoms by the operations associated to the connectives plus the fixed point operator. So note the difference, right? So in the standard syntax, the fixed point operator was part of the object language, right? It was a symbol of the modal language. Here, the fixed point operator is simply an operator on formulas. It's a meta thing. So we can, given a formula, we can form a fixed point. Yeah, and so what we have is that if you take d fixed point, the root of phi using lightning, and then you take the fixed point again, then you get phi. But note that it doesn't work in the other direction. So suppose you have a double fixed point, the fixed point with respect to P, the fixed point with respect to Q, and then box P and Q. If you lightning it with P, then you get box P and P. But that's not the same thing as the fixed point of Q for box P and Q, right? So one has to be quite careful here how to spin it. Yeah, and if you take phi and then take its d fixed point formula, and then you substitute phi for P, then you get again phi modulo bisimulation. And what you also see is that if you take a fixed point twice, that's the same thing as taking it once for when you identify the variables P and Q. So you see that in fact the syntax already has a kind of opinion about fixed points, right? So if you work in the language with the fixed point operator as a primitive operation on the object level, of course, you could say, well, it's a choice whether two fixed points in a row, taking two fixed points in a row is the same thing as taking one fixed point for the identified variable. So that would be kind of choice, but here it's built in the syntax that this happens. So the syntax has certain opinions, pre-programmed opinions about what is valid. Okay, so now we went through all this trouble, and you could think, oh, okay, it's rather complicated, but well, first I would want to claim, of course, that if you take a little bit of time to get used to it, then it's not complicated anymore. But we are now rewarded because the deduction system is extremely simple, right? We simply have the axioms and rules of K. We do have Löb's rule, and we do have that bisimilar things are equivalent. So now let's first, for a moment, zoom in on the third axiom, right? So the third axiom is not really, I would claim, it's not really an axiom. It's an artifact of our convenient choice of thinking modulo isomorphism primarily of the formulas. So then, of course, they're not identical, but in fact, they're intended to be identical, right? So the things modulo bisimilarity are analogs of the rational numbers, and so in fact, if you think modulo bisimulation, then this is just identity of the formulas, and so it's not an axiom at all. So it's really a trace of a design choice. Yeah. So now the interesting thing is, you know that K is closed under Löb's rule by a simple fixed point argument, and so you see. So in some sense, what we have here is simply the cyclic version of K. But of course, so if you leave out Löb's rule, you pull all the T. So the cyclic syntax without Löb's rule is in some sense powerless. So the Löb's rule in combination with the cyclic syntax is suddenly doing all kinds of work, right? So if you have the flat syntax and you just have K and Löb's rule, Löb's rule does nothing at all. If you have the cyclic syntax and not Löb's rule, then you get a rather very weak logic, and you really should add extra axioms. So the real actions happens by this combination of the cyclic syntax and Löb's rule. But so in some sense it is cyclic K, right? But then of course you could also say, well, cyclic K is the thing without Löb's rule. Okay, so now we have everything in place, and nice things are happening. So we can immediately define something good, namely, so I call that the Grullet modality. It's a kind of transitive closure. If you think of crypto models, so the box Grullet of phi is simply the fixed point of box phi and p, where p is fresh. And so, so the fixed point of equation for box Grullet is simply box Grullet phi if and only if box phi and box Grullet phi. Okay, okay. By the way, note here, right? So the if we would have done this on standard syntax, you would have for the box Grullet, there would have been a specific choice, a relevant specific choice of what the variable p is, right? And so there would be a box Grullet p for the choice p, and there would be a box Grullet for the choice Q, and it would be a theorem that these two are equivalent, blah, blah, blah. So you see the kind of malaise that you have if you use the standard syntax. And so, but here it's all good, because if you take another fresh variable Q, then the fixed point operator with respect to Q of box phi and Q is, the result is simply identical, right? So this P really only exists in the syntactic operation that we do, right? So the P really disappears by the application of the fixed point operator, and so there's no, it's just it's really a unique thing, modular isomorphism that we're looking at. So what we have is, of course, so the box Grullet satisfies the fixed point equation. It verifies Löb's logic for the box Grullet. What we do have is that if you prove, oh, this one should have moved up. It's not the Grullet principle. If you can prove phi if and only if psi, then you can prove d gamma p. You can prove that the fixed point of phi with respect to p is the fixed point with respect to psi, supposing, of course, that p is modularized in both phi and psi. And similarly, we have the Jongh-Sambin-Bernardi theorem that says that if we have the true, if we have p if and only if phi and box Grullet p if and only if phi, then we have that p is equivalent to the fixed point of phi, right? So then assuming modulization. So this one really should have been it's an insight, but you need the first one is in fact a lot of work, but of course you do want this, right? It says that the fixed points are independent of the specific choice of the formula modulo provable equivalence. Yeah. So the interesting thing is that we still have, so that we do not have the explicit fixed point theorem, so that's the Jongh-Sambin, but we do have the uniqueness of Gödel and Henkin sentences, and we have the general uniqueness of fixed points. You still have this thanks to the existence of the Grullet modality. Let's see. Wait a moment. Okay, maybe I'll go through this and then we could have a small break. Okay, so here I just took one example of specific reasoning, right? So why is the Grullet, does the Grullet modality give us all the wonderful principles that we want? So why, for example, does it commute? Why do we have the second Löb condition for it? Well, here you are. Suppose that we have box of the second Löb condition for the box Grullet. So that's this one, right? So the whole thing is, if you have Löb's rule, if you want to prove something, simply assume that you have it already under the box and then reason. So we want to go now from box Grullet phi arrow psi to box Grullet phi implies box Grullet psi. Okay, now how does that work? Well, first we apply the fixed point equation. So you go to box phi implies psi and box Grullet phi implies psi. Now, under the box we have it. So we use this one, plus of course the implicit use, all the implicit uses of K, and you get that we can replace this one by this one, right? We take the box Grullet through the arrow here. And now we rearrange this using proposition logic inside the box. That's of course using again K principles. So if we have this, then of course from phi and box Grullet phi, we have psi and box Grullet psi, right? So that's that one. Now we use, because here we have the simple box, right? Not the box Grullet. For that we have the second Löb condition. So we get this arrow through the box, and so we get box phi and box Grullet phi, box psi and box Grullet psi. And then we apply the fixed point equation again in the other direction, and you get box Grullet phi implies box Grullet psi, and that's what you wanted, right? And so all the other things are boringly like this. So you assume the provability of what you want. And yeah. So now you can prove, and then this is really, so I'm really smuggling, because proving this substitution principles is a lot of work. So that's and you really need guard induction to do it. So it's not simple. But you can prove the substitution principles. So the dot here inside the box means, so box dot means, box dot of theta means theta and box of theta, right? And simply similar for box dot Grullet. So we have the box dot Grullet of phi in if and only if psi. So if it's both truly and provably equivalent, then you can substitute modulo provably equivalence psi and chi for p in phi for any p, right? So that you don't need modulization here. But if you have modulization, then you can drop the dot here. And so if you have box Grullet of the equivalence, then you have the equivalence. And now you prove the Jongh-Sambin-Bernardi theorem. So suppose phi is modulus in P, then we have from the box dot Grullet equivalence of phi with P, so saying that P is a solution of phi, then P is simply the fixed point. Here you have to prove. So suppose that the box dot P if and only if phi, then, and now we suppose we want to prove that P is equivalent to the fixed point, and so we assume the provability of this. Now, suppose P if and only if phi. Now, so in phi here, P occurs, but we have the, it occurs modalized, and so we can apply the substitution principle for this one. And so we get that this is equivalent to phi, and the result of the substitution of the fixed point. And then we apply the fixed point equation, and you get the fixed point of phi. Now we can apply Löb's rule, but wait, we still have some material here that's not allowed. But you can prove that if this material that you have here is screened off by a box dot Grullet, then you are allowed, right? So that's in this case you may do it. So that's in fact the strengthened Löb rule. Okay, so Chair, do we want a small break, or shall I go on for 20 minutes and then stop? What is the preference of the audience?
So if it's only 20 minutes, I might continue, but what do people prefer? Can we get maybe, I don't know how to do this on Zoom. Maybe show your hand if you're prepared to have a break.
So is a 5 minute okay? 5 minutes okay. 5 minute break is okay?
Yes, 5 minute break is fine.
That's
all right, so let's do this. Let's have a 5 minute break.
Okay.
Okay. Okay, welcome back after the break. So yeah, so for the new, it's very nice that for the new cyclic language that everything that we know and love still works without any problems. So Kripke models are defined as usual, right? So the valuation, but to define the valuation function, you have to do a kind of double recursion, namely one on the depths of the world and guard recursion with respect to the box occurrences in the formula, right? Because the point is that, so if you look at the box occurrence, then you only need the values at the higher worlds. And so we assume that these are already given. And so the box occurrences are done. And then the box recursion is precisely what you have when you have the values for the box occurrences already, and then you can lift this to the rest. And so, in fact, so the guard recursion is precisely what you need, and the upwards well-foundedness is precisely what you need to define your Kripke interpretation. And since the box occurrences are preserved by bisimulation, the value is also bisimulation invariant, right? So we really have defined the forcing relation on formulas modulo bisimulation, right? As intended, of course. If this wouldn't have worked out, then we would have been dead. Yeah, so what about the completeness theorem? Well, there is, that's, yeah, still in a somewhat sad state. So we can translate the cyclic Henkin logic into the flat Henkin calculus on standard syntax. And I will talk about that a little bit. So HC is synonymous to the well-founded part of the new calculus. Yeah, I will say a bit about that in a moment. And so one thing that you can do is simply apply the well-known completeness theorem for the new calculus. And you get your completeness theorem on the finite upwards well-founded Kripke models. Done, right? Well, of course, the completeness theorem for the full new calculus, of course, allows also cyclic Kripke models, but of course we restrict ourselves to the well-founded part, and so that's okay. And alternatively, we can reduce the completeness question for the Henkin calculus to well-foundedness logic, and that's precisely the logic of box and box Grullet, but then without the fit point. So it's a well-foundedness logic is a bimodal logic, and you can reduce, but not by an interpretation, the Henkin calculus to that. Yeah, also a little bit sad is that the completeness proof for WFL seems to be completely clear, but it still also hasn't been worked out yet. But yeah, since we have it in two different ways, it's clear that it should be okay. So we do have our completeness theorem for cyclic Henkin logic on finite, non-transitive, not necessarily transitive, well, non-transitive upwards well-founded Kripke models. Well, it's a kind of similar to with arithmetical interpretation. So it was a little bit of a puzzle how to do the arithmetical interpretation, but it turns out that you can do it simply. So the definition is indeed very simple. Suppose you have some theory U and a provability predicate that I made it a gray box. Suppose that the gray box satisfies the first two Löb conditions plus Löb rule with respect to the theory. Then an arithmetical interpretation is a mapping from the nodes of phi to U sentences, and they satisfy the commutation clauses modulo U provable equivalence. So that's what you demand. And so that defines interpretation. So the definition of an interpretation, simple enough, but not clear, of course, that there are interpretations at all, that they exist. Now, suppose you have two interpretations for phi and psi, and suppose that the variable occurrences are going to equivalent sentences. And suppose that you have a bisimulation between the two, and suppose that it relates to nodes, then the values are the same. So you get that, that if you have an interpretation that it does respect bisimulation. So the interpretation, if it exists at all, then it is a mapping to the elements of the diagonalized algebra of U. Okay, and so there's also an existence theorem. So if we have a mapping F0 from the propositional variables of phi to U sentences, then we can find an arithmetical interpretation that coincides with F0 on the variables. So to do that, we need this, the multiple fixed point theorem in U to make it all work. And then you prove the existence again with guard recursion with respect to the box occurrences. So yeah, so it's a little bit of work to get it done, but yeah, it can. So nothing at all has been done. So that's a big terra incognita about the arithmetical completeness. It's interesting. So of course you can start with the cyclic mu calculus, sorry, the cyclic Henkin calculus, and then add Loeb's third principle, right? Box implies box, box. And so then our system becomes definitionally equivalent with Loeb's logic. It's really Loeb's logic that you have, but then with the cyclic syntax. And the interesting thing is that if you then that the Solovay argument, it's completely clear that the sentences that Solovay associates to the node really give you an arithmetical interpretation. So you don't need the whole thing with the guard recursion, etc. So the Solovay solution is immediately a solution for if you have the cyclic syntax, which is I found rather surprising. I thought it would be complex, but it turns out to be very simple. So the arithmetical interpretations work, but there's still a lot to be done. And of course, there are some examples that could be looked at. Yeah, but I do hope people will at some point pick this up and really try to work with examples. For example, from the standpoint of the Kripke semantic, it seems, for example, that we have that the Gödel sentences need not be definable, but if we go back right to the very beginning, you see that my example, my Gödel sentence was definable. So can we find an example where the Gödel sentence is not definable? The Kripke semantic says it must, that it is undefinable, but so is that reflected in the arithmetical semantics? That's probably the simplest kind of question to try to solve. Okay, so now the last part is, yeah. So David already thought of the question that I'm answering in the last part. So there is, so one of the great fixed point logic is Löb logic, right? And so that's the logic of guards, right? So the fixed points are saved from being paradoxical because we have guards. There's another approach to fixed point. The second great approach to fixed point is, say, positivity. So we demand that the fixed point variable only occurs in positive places. And if you do that, you get the mu calculus. And the mu calculus is a really big thing in computer science. There's a tremendous amount of research on the mu calculus. And yeah, so I only have scratched the surface of all that, but it's a lot. And so what is the fixed point calculus for? Well, for our purposes, it's as follows. We have the fixed point operator again, but now as part of the syntax. And so it's written mu because it's supposed to give you the minimal fixed point. And so there's what we have is not just the fixed point, the clause that says that it is a fixed point, but you have the minimality principle that says that if something is a prefixed point, then it's above the minimal fixed point, right? So if you have phi of p of alpha implies alpha, then we have the minimal fixed point is smaller than alpha. Okay, so now the interesting thing is, so this has a completeness theorem on finite Kripke models, but not necessarily well-founded. But you can define the well-founded part in a miraculous way, namely by simply taking the Henkin sentence. So the smallest, simply take the smallest fixed point of provability, and that's in fact the minimal Henkin sentence. And so adding the minimal Henkin sentence to the mu calculus gives you precisely the well-founded part of mu calculus. Now the surprising thing is, so I cannot go into the proof, which is, I think, extremely nice, because it's how do we get from negative to guarded and back? It's yeah, it's not rocket science. It's not super difficult, but I think it's a kind of still kind of miraculous thing that you can do that. So we take mu plus h, and that turns out to be synonymous with the Henkin calculus, and that's in turn synonymous with the cyclic Henkin logic. And so cyclic Henkin logic is in fact the well-founded part of the mu calculus. Yeah, so yeah, regrettably, I cannot go in the scope of this talk into how to prove this. Yeah, so the different ideas to do this were already lying around. So there was already work on, for example, that if you have mu calculus, that it's sufficient just to even without h, that it's sufficient to restrict yourself to modalized variables, which still should be positive, etc. And then if you have Löb's rule, the thing drops out. We do not need the positivity inside the box anymore, etc. Right? So the contribution of Tadeusz and me was simply putting these things together, and not all the individual ideas here were already in existence. Okay, and now the nice thing is that we can, given this insight, we can transfer results from mu to cyclic Henkin logic. For example, we have Kripke completeness, as I mentioned, and we have uniform interpolation. And that's, of course, uniform interpolation is quite a difficult theorem to prove. And so, and now we get it for free, right? So Marco Hollenberg and Giovanna D'Agostino proved. No, I think it was Marco Hollenberg proved uniform interpolation. Well, we don't have to worry about how this proof works, because it full automatically is transferred to cyclic Henkin logic. And so we have this very amazing theorem, uniform interpolation, also for the cyclic Henkin calculus. So yeah, now a lot is unknown here, and so it would be, because as you saw, it's a little bit ugly that I have to move first from the new calculus to the flat version of the fixed point theory, and then to the cyclic thing. And yeah, I do think that it's completely clear what the cyclic approach to the new calculus should be. Namely, you simply have the cyclic syntax, but you replace the guard condition by simply the condition that the number of negative transitions on a cycle should be even. And I think that really is all there is to the new calculus. And so if you look at the treatments of the new calculus, you see that the new people are always wrestling with the binding of the variables. They really need ugly conditions, etc., and normal forms, etc. And that all disappears if you simply have the cyclic syntax, because the new operator becomes a meta operator. It's not really there anymore. And so, yeah, many things would be more beautiful, and hopefully it would be easier to directly compare the new calculus with the cyclic Henkin calculus, and in their own terms of the cyclic syntax. But yeah, nobody ever tried this further development, so it's completely open what it is going to be. So again, I hope that people would want to look at these things, because I'm really curious how this would work out in the end. Okay, that was it. So that's
all right. Thank you very much for this interesting talk. Let us thank the speaker. And now we have time for questions. So who would like to start?
May I have one question?
Yes, of course.
Yes. So before, so thanks for the good talk, which is a pretty interesting, especially for people like me who do not know the field in detail beforehand. And I briefly have some time reading your paper appeared this year before a talk, in which you also mentioned a possible connection between the cyclic formulas with cyclic proofs. Do you have any do you have any explorations already in this field?
No, yeah, right. So the whole thing is so the existing. Yeah, I forgot to mention that, right? So there is a lot of research on cyclic proofs also for for Löb's logic, and so yeah, my expectation would be that would be the really natural way to also set up a proof system, of course, for the cyclic Henkin logic. But yeah, again. This has not been explored further, as far as I know, right? So in my Moscow talk, I really tried to get people to look at that, but as far as I know, nobody has tried it yet. So, but it would be extremely interesting, because the cyclic proofs and the cyclic syntax feel like soulmates, and so they really should collaborate together. Yeah, but so yeah, the answer is regrettably no. So there's no unless someone is working on it and didn't communicate it. I don't know. So that would be also kind of very interesting thing, right? So to integrate the two cyclic approaches.
Yes, thank you.
Thank you. Any more questions?
Yeah, if now the people asked, yeah, I have some question. By the way, I missed one slide. So what is the language of this safe air? I mean the syntax.
Sorry, which slide did you miss?
About the language of CHL. About the syntax.
Wait, I'm going back. Yeah, so the language, so the language is simply all graphs, and so this is the definition of a graph, right? It's rather unreadable, but if you picture it in your mind like this, it becomes a completely clear thing, right? So so it's simply all graphs that are labeled by the connectives, and that satisfy the guard condition, right? So we only allow cycles on which the box occurs. So that's the syntax.
So you mean that in syntax is contain a graph as part of the language? That I'm pretty sure that the graph is a model.
No. The graphs are the syntax.
Okay. Okay. Okay.
Yeah, right. So the point is, yeah. Okay, well, we could discuss the ins and outs of the idea of syntax for hours, but yeah, I submit that the graphs are the syntax, right? So they're, and I think also in the case of ordinary predicate logic, there's, so the inductive way of viewing the syntax there has had too little opposition in my feeling, right? I do not believe that the inductive way of viewing the syntax of predicate logic is correct. It has, because the notion of binding is not represented in a good way there. But yeah, so the graphs are the syntax. That's the slogan here.
Wait, may I follow up? And what is the correct way to represent first order logic formulas?
Well, I don't quite know it, but so my favorite way is that it's graphs plus an equivalent, very roughly the graphs, but instead of the names of the variables, we have an equivalence relation for the sameness of the binders and yeah, so that's in fact the notation that was invented by Peirce and reinvented by Quine, and then again reinvented by Bourbaki.
Okay.
Yeah, I think that syntax is more correct because it treats it the correct way, right? So the usual way to do that is inductively is really that you say the true objects are the formulas modulo, the inductively generated formulas modulo an equivalence relation, which is in computer science called alpha equivalence or alphabetic congruence or whatever, right? So that's yeah. But of course that's not, but at least what I want to say is that the graph way of looking at formulas is definitely a decent one. And I think in linguistics there are also things like constraint-based grammars, etc. Right? So people have different ways of looking at syntax, not just looking at it as inductively generated. And in fact, the way, so if you think about the Peirce-Quine-Bourbaki idea, it's co-inductive, right? Because you have you have a deterministic way of breaking formulas down, but you don't have a deterministic way of building formulas up, because you have non-deterministically provide links between variable occurrences. But yeah, so that's yeah. So yeah, Jongh. So the answer is simply the syntax is the graphs.
Okay.
Yeah, I think there's a philosophical idea behind it too, but of course I'm just talking about the technical side here.
Okay, thank you.
And
yeah, I have another general question. Yeah, we know that the Löb's condition, Löb's 3 condition is a sufficient but not necessary condition to prove G2. And for your work, what's the relationship of your safe air with the G2? I believe your work on safe air has some motivation about the G2, right?
Yeah, right. So the yeah, so I didn't talk about that at all, of course. So the yeah, you can prove a kind of general version of the second incompleteness theorem, in which you ask for uniform representability of the axiom set. And so that uniform interpretability means that for every finite set of axioms, you have an extension to a bigger finite set of axioms, so that that bigger finite set of axioms verifies that each of its axioms is an axiom, right? So that's the uniform thing. And so you get this, the second incomplete theorem plus Löb's rule in that setup without problems, but you do not get, and you can in fact give counterexamples like the counterexample I gave here, that you do not get the third condition, right? Provable implies provably provable. Yeah. So there's a kind of general setup for the second incompleteness theorem that gives you CHL, but it doesn't necessarily use the third Löb condition. Of course, the spirit of this, the ghost of the third Löb condition is still there in this proof, because I do use the third Löb condition, but then not for the provability predicate that you are studying, but for another one. So there's still smuggling. There's still, it's not third condition free. I mean, the result is third condition free, but the proof is not third condition free. So you use the ordinary Gödel proof, but for another provability predicate to do it.
Yeah. Over safe air, the G2 also holds. So maybe it's not a very non-standard probability logic. For the non-standard probability logic, maybe the G2 just fails.
So I don't quite. So can you repeat the question slowly?
I'll just say another way. That's just You think that compared to GL, safe air is quite different from GL because it has not property full, but it still have the Löb's rule and can prove G2. So it's for me that it's not a very totally no standard probability logic. For me, that no standard probability logic means that he can prove the negation of G2 or G2 fails, or that he can prove that negation box and just the consistent of just a consistent statement.
Yeah, well, okay, you can, yeah. So I still again didn't understand everything you said, but so there are of course interesting logics where G2 fails. And yeah, the most interesting one is due to Volodya Shavlukov, who studied the logic of the Pfefferman predicate, the bimodal logic of ordinary provability and Pfefferman provability. And in this exciting logic, of course, the theory proves its own Pfefferman consistency, right? So Pfefferman invented this extremely useful notion of provability that is not sigma 1 anymore, that where the theory, the extension of piano proves its own consistency. And so there, and so yes, there's an extremely beautiful paper by Volodya Shavlukov in which he gives both arithmetical and modal completeness theorem for that. And yeah, so I always try to encourage people to read that, because I think the paper has been a little bit too little known for yeah, its extreme beauty. So do read the paper by Volodya on this. You're right, but yeah, there are of course lots of these things, but very often the provability logic of the non-standard proof predicates is not all that interesting, right? So if you take the Rosser predicate, so you almost have no interesting, so then you do have the failure. So the theory does prove its own consistency, but you don't have nice, you have also the second Lob condition fails, for example, right? So it's a kind of horror from the modal point of view, but the Pfefferman predicate is okay. Does that answer your question?
Yeah. I think, yeah.
I have understood it.
All right. Do we have any further questions?
Can I have another one?
Sure. May I ask what time are we? Do we have to close?
I think 12 is the limit.
Yeah, I heard 12, right? Yeah, so there's plenty of time for questions. So go ahead.
Okay, thank you. I'm pretty curious to the special operator in the syntax, the flashlight, and so by phi flashlight p, it seems that we break all the identical backlinks from leaves to the root and feed them to actually different occurrences of the same new variable p. So it seems to me, I'm not sure whether I understood that part correctly, but it seems to me that the flashlight is something like you in one time break all these backlinks instead of.
But just for the root, right? Just for the root.
Well, so if we have the graph, which is the formula in which the root is fed by two different identical backlinks from two different leads. Then after doing the flashlight, it will be fed the occurrence of the same new variable p instead of different new variables.
Yeah. Yes. So wait a moment. So we have the root, right?
Yes.
So now we break the links, but so we, of course, we keep copies of the. It's important that we keep copies of the root, right? So the root. So if you have n incoming things, then so each incoming arrow is made loose, but you provide a new endpoint, right? So the root. So if there's n incoming links, there are n new nodes, and they're all labeled p, right? So I think that if I understood what you're saying, so the whole point is, of course, that this operation, so of course the operation makes no sense when you use a variable that already exists, right? So I don't know what it would mean then. But you could also use a Q here, and then you get another formula. And so they're not they're not bisimilar anymore, right? So that's and they're not isomorphic anymore. You get it. So in fact, so the D fixed pointizing operator, breaks in. But so yeah, you're right. So I think now I understand your question. So you have to break all links, right? So you could imagine maybe a flash, a lightning flash that only breaks a number of designated links. But that, yeah, I haven't really thought about that, right? So that would be nice because you could maybe so you have so this kind of phenomenon, right? So the point, of course, here is that so if you have box P and Q, so then of course the fixed point operator, this one creates a loop towards this Q, and the Q disappears, right? It's identified with the root, and the variable is thrown away. And then we do it again, and we make a loop to the first, right?
Right.
And now if we break this, we have to break both loops. And that's the reason why this becomes box P and P, right? And so it doesn't just break, it doesn't just break the link that is created by this fixed point operator, which you would expect, in fact, because you would hope that this would be, that it would really be an inverse to this one, but it isn't, because there was already a looping present, and you break all loops. Yeah. So indeed, if you would have built a mechanism where you could target certain cycles to break and others not, you could do what you want. And in fact, I have to admit that I was completely confused by this because you don't expect this phenomenon, but it's there. So it's, as you see, so in one direction. So if we break all the links and we place them by P, and now we store all the links with the things labeled P, then of course you go simply back, right? So it's okay. But in the other direction, if you create links and you in a number of steps and you go back, then of course you get you don't just cancel the last step, but you cancel all steps. Is that what your question was? At least it was in the general environment of your question, I think.
Yes. Well, we have to confess that it's a bit hard to communicate. Yeah, sure. It sort of answered my question. Thank you.
Yeah, well, you could try again.
I think it's more or less just the feeling or a comment rather than a question. I'm thinking of if we sort of allow the flashlight to break the selected backlink arrow instead of all of them, that might sort of increase the expressive power of the language, and therefore it's sort of possible to describe things in more detail. Although I'm not sure whether this will make any essential use for what the work is devoted to.
Yeah. So of course the flashlight is a meta operation, right? It's not in the language, but indeed, at least the things we could say about the language get more refined. But I didn't yet meet an application of the idea, but it could very well be that closer study of what's going on that really could could do it, right? But it's,
Right.
but yeah, but one would have to think about how to implement this flashlight, right? Because we really should be able then to point. Well, maybe maybe you simply should look at a set of. It should have us input a set of links or something. Yeah. Okay. Well, maybe it's feasible, and as far as I can see, it could very well be useful, but I haven't met the application yet.
Thank you. Thank you.
All right, any more questions?
Maybe last very short question. Just compared to GL, does CHL has any property that GL has? But no. Does the CHL has any very important property, but GL does not have? But GL does not has. Except for arithmetic and completeness theory, since you have not explored. I mean, besides this, is any property CHL has, but GL does not have?
A good question. So, so we do have uniform interpolation. So that's beautiful, of course.
Yeah.
Wait a moment. Property. So yeah, it looks that, of course, so it doesn't have the explicit fixed points, and GL does have them. Yeah, I don't know a good example of a property it has in a superior way. Of course, if you look at the version of GL that you get here, you don't need, we only need Loeb's rule, right? So if we add 4 to our system, to cyclic Henkin logic, so CHL4, or maybe we could call it CGL for cyclic Gödel. Then you don't need to specify the, oh well, no, that's also the same. So because we can prove Loeb's principle as soon as we have 4 and Loeb's rule. Yeah. Yeah, I'm not sure. So if you look at the kind of decent mathematical properties and not silly examples, I wouldn't know. It's a good question, very good question.
Okay, thank you. Yeah. Since that it has many similars, it also has the finite model property. CHL.
Yeah. Well, in fact, my point here was really that it has amazingly many properties that GL also had, right? It's much better than when I discovered the system, it's much better than I ever expected. And also the kind of fun connection with new calculus. Yeah, maybe that would be an example, right? It has this beautiful, more beautiful connection with the well-founded new calculus, right? Because GL is just the transitive upwards well-founded part. And here we have you really get the well.
All right, so I think this is a good place to stop. I already asked my question during the break. So let's give Albert another hand.
Thank you for being a nice audience.
Thank you very much for a very nice presentation and discussion.